So hello everyone, welcome to the channel. So in this video, we're going to talk about the Radar Vegetation Index monitoring using Sentinel-1 SAR Imagery in Google Earth Engine. So now let's get started. So monitoring vegetation health and biomass dynamics is crucial for ecological studies, agriculture and climate change assessment. The optical remote sensing has traditionally been in the primary tool for vegetation monitoring, but synthetic aperture radar provides a unique advantage due to its all-weather capability, day and night imaging capability, and this study leverages the Sentinel-1 SAR data in Earth Engine to compute and analyze the Radar Vegetation Index, an essential indicator of vegetation structure and density. And let's talk about the dataset that is Sentinel-1 SAR GRD C-band synthetic aperture radar ground range detected log scaling. So the Sentinel-1 SAR GRD is a dataset produced by Sentinel-1 mission, part of the European Union Copernicus program. The Sentinel-1 consists of a constellation of two satellites, satellite that is Sentinel-1A and Sentinel-1B, which carries the C-band synthetic aperture radar instrument. So these satellites are designed to provide high resolution, all-weather, day and night radar imaging for a wide range of applications, including environmental monitoring, disaster management, and land use mapping. So now let's talk about the key characteristics of this dataset. So the C-band radar, the Sentinel-1 uses C-band radar, which operates at the wavelength of about 5.6 centimeter. This wavelength is ineffective for detecting surface features changes, especially in agricultural fields and urban areas and forest and water bodies. The synthetic aperture radar SAR technology allows the satellites to generate a high-resolution images by combining multiple radar signals over a time period as it moves over the Earth's surface. This is essential for achieving a fine spatial resolution even when imaging the larger areas. So GRD product, so ground range detected. So the GRD product is a level 1 SAR image that has been processed to correct for the terrain and other distortions, making it suitable for a direct analysis. It represents the radar backscattered from Earth's surface and providing information about the surface roughness, moisture intake, moisture content and other characteristics. And log scaling, the backscattered value in GRD product are expressed in decibels using log scaling, which helps in enhancing the visualization and interpretation of radar signals. This scaling also reduces the dynamic range of data, making it easier to analyze. So in the next step, we're going to talk about the polarization. So before that, I'm going to introduce the code. So we're going to generate the radar vegetation index using Sentinel-1 SAR image. So for that, first we have to define a region of interest. So you can able to visualize from this the map here. So this is my region of interest. So you can able to see this is my region of interest I have created. So let me turn off other layers here. And to create your region of interest, let me click to a satellite mode here. So basically we're going to cover this particular, any part of the, we can analyze this particular radar vegetation index for any part of the world. So this is a global data set. And for example, I'm going to select this particular study region. And now to create a region of interest, first we're going to navigate this option called draw a rectangle. So once you did that, you can draw a rectangle over any part of the world. So for your chosen study region, for example, I've selected this particular area as my study region. So I'm going to draw a rectangle over this study area. So once you did that, a new variable called geometry pop up here, a polygon with 4 vertices. So here I'm going to click this option called show generated code. So in this generated code, we have this latitude and longitude of the newly created study region. So I'm going to copy it using Ctrl+C in my keyboard, and I'm going to close this, and I'm going to paste it my value here. So in this variable called study area coords, that is coordinates, and I'm going to select this coordinates, and I'm going to click Ctrl+V in my keyboard to paste the latitude and longitude of my newly created study region. So once you did that, I'm going to click this option called exceed, and I'm going to turn this off. And the next step, I'm going to convert this latitude and longitude coordinates into a polygon geometry. So to do that, we're going to define another variable called study area equals to earthengine.geometry.polygon study area coords. So referring to this particular variable containing the latitude and longitude of newly created study region. So next step, we're going to center this particular boundary. For example, we have selected this as our new study region. And to center this, we're going to define map.center object study area. And we have to set a suitable zoom level according to your choice. For example, so my choice for zoom level is around 11, which is suitable for my analysis. So you can change the zoom level according to your choice. And in the next step, we have to add this layer to Earth Engine. So to do that, we're going to define map.addLayer study area and with the default visualization parameter. And we're going to output the layer name as study area 1. So in our next step, we're going to load our Sentinel-1 SAR Imagery into Earth Engine. So to do that, we're going to define a variable called Sentinel-1 collection equals to Earth Engine, Earth collection Copernicus S1 GRD. So let me explain about this particular dataset. So this is Sentinel-1 SAR GRD C-band synthetic aperture radar ground range detected log scaling. The dataset availability is from 2014 to 2025. And dataset provider is European Union ESA Copernicus. And using this code, you can access this particular dataset. And the revisit interval of this particular dataset is around 6 days. And the bands, these are the following bands that is available in this dataset, starting with HH, that is of single co-polarization, horizontal transmit and horizontal receive. And the resolution of this particular band is around 10 meters. And the second band is HV, that is dual band cross polarization, horizontal transmit and vertical receive. And the next band is VV, that is single co-polarization, vertical transmit and vertical receive. And the spatial resolution is around 10 meters. And last is the VH band, that is 10 meters and dual band cross polarization and vertical transmit and horizontal receive. And the last band is of angle, which is in unit is in degree, and other bands are in the units in decibels, so you can able to see the units. So this particular band has a units in degree and the resolution is around 20,000. Approximate incident angle from ellipsoid. So now let me get back to Earth Engine. So in the next step, we have to filter with a specific timeline. So we have to fix our analysis period. For that, we're going to use this function called .filterDate function. So using this function, we can filter the specific timeline. So the dataset availability starts from 2014 to 2025. So our period of analysis is between 2020 to 2024 December 31st. So to do that, we're going to define .filterDate 2020 January 1 December 2024 December 31st. So now we have selected the time range for our analysis. So in the next step, we're going to filter with based on our region of interest, that is our study region we have created here. This is our region of interest we created. So to filter based on our region of interest, we're going to define .filter bound study area, which refers to our region of interest, referring to this particular variable. And in the next step, we're going to filter based on the transmitter receiver polarization. So let me explain about this VV. So polarization, so dual polarization. Sentinel-1 GRD data typically includes two polarization mode, that is VV, that is vertical transmit and vertical receive. And the second polarization is VH, vertical transmit and horizontal receive. So these polarization provides a different perspective on surface scattering properties, which are useful for distinguishing between different types of land covers. And about VV polarization, vertical. So in VV polarization, the radar transmits vertically polarized wave and receiver also detects the vertically polarized component of backscattered waves. This means both transmitted and received signals are vertically polarized. And interpretation, so in an image, areas with a high VV backscattered appears brighter, indicating the surface that are rough or have a lot of vertical structures. Conversely, the low VV backscattered appears darker, typically indicating a smooth surface or open water. And the second polarization is VH polarization, vertical horizontal. So in VH polarization, the radar transmits vertically polarized waves and receives the horizontally polarized components of the backscattered wave. This cross-polarization mode detects the part of the signals that changes orientation upon interaction with the target. So interpretation about this is a high VH backscatter typically indicates the areas with significant vegetation or the complex surface feature that causes a multiple scattering and depolarization. So the low VH backscatter suggests a simpler surface with less depolarization, such as bare soil or spare vegetation. So let me get back to Earth Engine. So next, we're going to ensure the VV polarization is available. So we're going to filter it based on the transmitter receiver polarization VV. So to do that, we're going to define dot filter Earth Engine dot filter dot list contain transmitter receiver polarization VV. VV is the vertical polarization, and next is we're going to see for VH polarization availability of VH polarization. So to do that, we're going to define dot filter Earth Engine dot filter dot list contains transmitter receiver polarization. So VH. So now we are ensuring VH polarization is also available. So you can also check the metadata of this particular Sentinel-1 SAR imagery. So to do that, we're simply gonna mention print filtered Sentinel-1 collection and Sentinel collection, referring to this particular variable that is our Sentinel-1 SAR imagery. So I will explain it before I will explain the next, that is the instrument mode. So let me explain about what is the instrument mode is. So IW, which represents the interferometric wide. So interferometric wide swath. So interferometric wide swath mode is one of the primary operation modes of Sentinel-1 synthetic aperture radar instrument, which is used for a wide range of Earth observation application. This mode is specifically designed to capture the high resolution imagery over a wide area, making it suitable for applications such as land monitoring, oceanography, and disaster response. So the polarization. So IW mode can capture data in both single polarization and dual polarization, like VV plus VH or HH plus HV. The dual polarization capability enhances the ability to differentiate between different types of land covers and surface conditions. The common use of VV and VH polarization in IW mode allows for a more comprehensive analysis of the surface feature, as it can capture both vertical and vertical horizontal scattering information. As the name suggests, the IW mode is optimized for interferometric applications, so it enables the generation of interferograms, which are used to measure the surface deformation, topographic changes, and land subsidence with high precision. So we're going to select filter based on the instrument mode. We're going to select the interferometric wide swath. So to do that, we're going to define dot filter Earth Engine dot filter dot equal instrument mode equals to IW. So IW is interferometric wide. So once you did that, in our next step, we're gonna apply the orbital property pass. So let me explain about this orbital property pass. So we have two different types. One is ascending and the second type is descending. Let me explain both those types. So the orbital properties of Sentinel-1 SAR imagery, ascending and descending passes. So Sentinel-1 is a constellation of synthetic aperture radar satellites operated by European Space Agency, designed for a continuous Earth observation. It consists of two satellites, Sentinel-1A and Sentinel-1B, that provides the coverage of entire planet with a high temporal resolution. These satellites operate in both ascending and descending orbital paths, allowing for more comprehensive monitoring of Earth's surface. So understanding these passes is essential for interpreting the SAR imagery accurately. So first is the ascending pass. An ascending pass occurs when a satellite moves from south to north, passing over the Earth's surface. This generally means that the satellite is moving from a lower latitude to a higher latitude, typically during the local night or early morning hours. So orbital path. During an ascending pass, the satellite orbit takes it from the southern hemisphere to the northern hemisphere. The ground track of the satellite moves from west to east due to the rotation of Earth. So the second pass is the descending pass. A descending pass occurs when the satellite moves from north to south, generally passing over the Earth's surface during local daytime or afternoon. In this path, the satellite travels from a higher latitude to a lower latitude. So orbital path. During a descending path, the satellite orbits moves from the northern hemisphere towards the southern hemisphere. The satellite travels westwards in its orbit while the Earth rotates eastwards beneath it. So the short description about the ascending path and descending. So ascending path, this occurs when a satellite moves from south to north, and during this path, the satellite captures the image while it is ascending from a lower to a higher latitude, and the local solar time for the ascending path typically falls in late afternoon or evening. And in case of descending path, this occurs when the satellite moves from north to south, and during this path, the satellite captures an image while descending from a higher to lower latitude. The local solar time for the descending path typically falls in early morning. So let me get back to Earth Engine. So now we're going to select the orbital property pass as ascending. So to do that, we're going to define dot filter earth engine dot filter dot equal orbital pass property equals to ascending. So we're going to filter based on ascending orbit image. And in the next step, we're going to select this following two bands, that is vertical polarization and vertical horizontal polarization for our analysis. So to do that, we're going to define dot select VV and VH. So VV, which represents the single co-polarization, vertical transmit and vertical receive, and VH, which represents dual band cross polarization, vertical transmit and horizontal receive. So in the next step, we have to visualize the detail about this particular dataset. So to do that, we're going to define print filtered Sentinel-1 collection and Sentinel-1 collection referring to a variable. So now we can visualize the metadata property of this particular image. So let me navigate this option here. In the console section, let me reset this. Let me run this. So in the console section, you can able to visualize we have filtered Sentinel-1 collection, image collection Copernicus SGRD. We have 332 elements for the specific timeline, that is from 2022 2024 December 31st. So now here we have this type, ID, version and bands. Features, we have around 323 elements. So for example, I'm going to select this particular image here. So we have two bands, that is VV and VH. So we have selected VV and VH. And the properties, so we have this variety of different properties that is available here. For example, instrument synthetic aperture radar, and instrument mode IW, and instrument swath is IW, and the orbital property pass is ascending. So we have selected based on the metadata here the orbit properties pass. So we have selected ascending. So in this way, you can able to visualize the metadata property of this particular image. So we have total of around 323 elements available for the specific study region, images available. So in our next step, we're gonna compute our RVI, that is Radar Vegetation Index, for each image in this image collection. So let me explain about the Radar Vegetation Index. So let's talk about the Radar Vegetation Index. So Sentinel-1 mission, a part of our Copernicus program, provides a higher resolution SAR data in C-band with vertical transmit and vertical horizontal transmit polarization. So Radar Vegetation Index is a key SAR derived index used to assess the vegetation cover. It is computed using the formula. So that is RVI equals to 4 multiplying VH, that is vertical horizontal polarization, divided by vertical horizontal plus vertical polarization. So this formula utilizes the dual polarized backscatter intensity to characterize the vegetation structure. So higher RVI value, which indicates the dense and healthy vegetation, while the lower value suggests spare or non-vegetated areas. So now to compute the Radar Vegetation Index for each image in the image collection, so we're going to define this variable called RVI collection equals to Sentinel-1 collection dot map function image. So now we're going to create a loop function. Inside the loop, we're going to create a variable called sigma equals to earth engine dot image 10 dot power image dot divide by 10 So basically it converts the Sentinel-1 backscattered values from decibels to linear scale. So the radar backscatter data is generally stored in decibels, but for many radar analysis algorithm, it requires a linear scale value. So the linear scale value allows the accurate statistical analysis and filtering and modeling. So basically this line of code that converts a decibel values to a linear scale to perform any analysis. So next we have to compute our radar vegetation index using the formula RVI equals to 4 multiplying vertical horizontal polarization divided by vertical horizontal polarization plus vertical polarization. So to compute this formula, we're going to define a variable called RVI equals to sigma dot expression. So expression 4 multiplying VH divided by VH plus VV. So we're going to relate the VH VV. So we are referring to VV is vertical polarization. So for that, we're going to define sigma dot select VV. So we are selecting vertical polarization band, and similarly VH sigma dot select VH. So sigma refers to this variable where we converted the decibels to a linear scale value, and VH is sigma dot select VH. So VH is the vertical horizontal polarization band, and last we're going to rename as RVI, that is radar vegetation index. So in the next step, we're going to apply the 30-meter focal median filter for the noise reduction. So for that, we're going to define this variable called RVI smoothened equals to RVI dot focal median. So we are applying this focal median function 30 meters square meters. So the square here which represents the window size, that is the window size in square, and which is represented in this meter, represented in meters. So we are applying this to remove the speckle noise common in radar image. For example, in Sentinel-1 SAR image, so it smoothens the RVI radar vegetation index without losing the important details, and preserves the edge and sharp features better than mean filters. So the next step, we're going to copy the time properties and return the processed image. So for that, we're going to define return RVI smoothened dot copy properties image system time start and system time end. So it copies the metadata from the original image and ensure that the processed image retains the original timestamp. So in our next step, we're going to display the mean radar vegetation index image for the time period. So we're going to display the mean radar vegetation index image for the time period from 2022 to 2024. So for that, we're going to define map.addLayer RVI collection.image mean function. So to obtain the mean RVI image for the time period from 2020 to 2024, we're going to define the statistical function called mean function, and we're going to clip based on a region of interest. So for that, we're going to apply dot clip function. Inside, we're going to mention our study area, that is our region of interest, and we're going to set the minimum value of 0 and to a maximum value of 1. And these are the following color palettes: blue, green, and yellow. So the yellow which indicates the highest RVI value, and the green which indicates the moderate RVI value, and the blue which indicates the lowest RVI value. And we're going to output the layer as mean RVI. So now let us visualize the results. So we're going to navigate this option called run and click run. So in the layer section, I'm going to turn off other layers here. So this is our RVI, that is radar vegetation index for the study region. So you can able to see here. And now let me turn to a satellite mode here. And I'm going to turn this, adjust this transparency of this layer here. So you can able to see the base layer here. Let me turn this off. So you can able to see here clearly. So this is our base map, and this is our mean RVI value for the over the time period from 2022 to 2024. That is radar vegetation index. So based on the RVI value, the higher RVI value indicates the dense and healthy vegetation, while the lower value suggests a spare or non-vegetated areas. Let me get back to Earth Engine. So we're gonna click this option called Inspector tool here. So we're going to click here, this value, and we're going to visualize the value here for the specific farmland. So here you can able to visualize in the inspector tool the mean RVI value we have around the value of 0.39, the mean RVI value for this farmland. Similarly, let me check over the RVI value over this water body. Let me check with the base layer here. So you're gonna click this and visualize the value here. So you can able to see over the water body, the value for radar vegetation index is kind of lower here. So, it's around 0.13. And similarly, let us place our inspector tool over this river course here. I'm going to place my value here and let us visualize the values. Let me place it once more time here. So mean RVI value, so it is around 1.057, so which indicates a high RVI value. Similarly, let me check over this farmland here. So it has a value of around 0.4. So higher the RVI value, which indicates the dense and healthy vegetation, and the lower the RVI value, which indicates the spare or non-vegetated areas. For example, the water body that is available here, let me click and visualize the value here, which is around 0.317. So let me get back to the console section here. And the next step, we're going to define a smaller region for our time series analysis. So again, we're going to define within the study region, we're going to specifically focus on a particular farmland. So for example, let me select this sub-region here. Let me show you that. So you can able to see here. So you can able to see here, I've created sub-region within the study area, which is simple as we said previously. We're going to navigate this option, draw a rectangle. So you can draw a rectangle over any farmland of your choice here, and using this option here, draw a rectangle. And with similar procedure, once you draw, we have to copy and paste the latitude and longitude of this particular study region and paste it here in this variable sub-region coordinates. So once you copied and paste the latitude and longitude of your newly created sub-region, that is your farmland of your choice within the study region. So next we have to convert that to a geometry polygon. So next, to convert this above given latitude and longitude to a polygon, so for that we're going to define this variable called subregion equals to earthengine.geometry.polygon subregion coords. So we are referring to this particular variable containing the latitude and longitude of the study region, that is our subregion. So we are specifically focusing on this particular farmland here. You can able to see. So I have drawn a rectangle. We're using this particular tool, that is draw a rectangle. So I have drawn a rectangle over this farmland. So to analyze the radar vegetation index over this particular farmland, so for that we have drawn a new sub-region within our study area. So this sub-region is our farmland. So next, to add this layer, we're going to define map.addLayer sub-region with the default visualization parameter, and we're going to output the layer name as sub-region. So next, to create a time series chart analysis for our radar vegetation index. So for that, we're going to define print ui.chart.image.series, and image collection we're going to refer VRI, that is RVI collection, that is radar vegetation index, and the region we're going to mention the sub-region. So sub-region is this particular study region. So you can able to see from this layer here. And the reducer, we're going to apply the reducer function, that is we're going to apply the statistical function those in order to apply the mean radar vegetation index value. So for that, we're applying this dot main function. So for reducer section, we're going to mention earthengine.reducer.main function. And last, we have to specify the spatial resolution of this particular dataset. So for example, this particular dataset is a Sentinel-1 SAR Imagery. So it has a spatial resolution of around 10 meters. So for that, we're going to mention here as 10 meters. And X property, the system time start. And last, to set some options to our time series chart, we're going to define this function called dot set options. Title, we're going to mention radar vegetation index time series. And the v-axis, we're going to specify RVI. And the h-axis, we're going to specify as the year. And the color series, we're going to mention the color and green. The point size mentioned is 3. This is the point size here, so you can able to see I have mentioned it as a 3. And similarly, so to be also we're gonna generate a time series chart for our backscatter time series for vertical polarization and vertical horizontal polarization. So to generate the time series chart for backscatter time series for VV and VH, so we're gonna apply the similar steps. Print ui.chart.image.series image collection. Here we're going to refer to Sentinel-1 collection, and the region again we're going to mention the subregion. So this is our subregion here, and the reducer I'm going to mention earth engine.reducer.main function, and the spatial resolution is around 10 meters. And the system property, that is x property, is system time start. And again, to set us options to our graph, we're going to define dot set option function, and in that we're going to define title Sentinel-1 VV VH backscatter time series as a title for time series analysis chart for the VV and VH. And for v-axis we're going to mention backscattered in decibels, and then h-axis we're going to mention the title in year and the series. So we're going to mention the blue color for VH, that is vertical horizontal, and for VV we're going to mention as orange, and the point size we're going to mention as 3. So now let us take a look at the chart here. So you can able to see from here, this is the time series chart. So now we can clearly able to visualize it here. So this is a time series chart for Radar Vegetation Index time series. So this is Radar Vegetation Index. The value starts from 0 to 1. And similarly, the Sentinel-1 VV VH backscatter time series. So it starts from the backscatters in units in decibels. Starts from -40 to 0. And this axis is represented in year. So now let us take a look at this chart here. So I'm going to click this option here. So now we are currently visualizing the radar vegetation index. So you can able to visualize the value ranges from +0 to +1 here. So the positive value which indicates the higher RVI value. So higher RVI value which indicates the healthier and dense vegetation, and the lower value of RVI which indicates the spare or non-vegetated areas. For example, the higher value which is indicated here, so which is around in August 2, 2023, so has a RVI value of around 0.903. So highest level of value is observed here. And similarly, the lowest RVI value is observed during this year, that is in February 2020. The RVI value was around 0.25. So we can able to visualize there is a RVI value varies from 0.3 to 0.9, so which indicates the seasonal variation. And also you can able to see from this graph here, so in the month of July, for this study region has a higher RVI value, and in the month of February, so it has a lower RVI value. Similar trend was observed, you can able to see from here. So, and also similar trend, higher RVI value was observed during August, and similar low RVI value was observed in this month. And during this sort of month in July is higher. So you can able to see the cyclic fluctuations. It's a seasonal fluctuations you can able to see from here. So let us take a look at the interpretation of this particular chart here. So RVI value fluctuates between approximately 0.3 to 0.9, indicating a seasonal variation in the vegetation density. So higher RVI value suggests a denser and healthier vegetation, whereas the lower value indicates spare vegetation or non-vegetated surface. So the graph exhibits a clear seasonal pattern with RVI peak occurring around the mid-year in April, July and October, likely correspondingly to the period of higher vegetation growth. And the RVI declines indicates a vegetation, so which might be indicating the harvesting time of the seasonal dry condition. And a notable peak in 2023 suggests a period of higher biomass, possibly due to increased precipitation or agricultural activities. So let me get back to Earth Engine. And also you can download this particular graph as a CSV file by clicking this option here called download CSV. So in this way you can download this. So I'm going to mention this as a RVI, and I'm going to click save to download that CSV file. And let us check this out here. So we're going to open this. So now here you can able to visualize here. So we have the time and the RVI value for the each month from the over the period from 2020 to 2024. So you can able to see here. So in this way you can download it as a CSV file too. Let me get back to Earth Engine. Similarly, we have this our second graph, Sentinel-1 vertical polarization and vertical horizontal backscatter time series. So this graph is represented as backscattered in decibels, and this axis in year. So the time range from 2020 to 2024. So now let us take a look at this chart here. So the color orange, which indicates the vertical polarization backscattered, which is represented in decibels, and similarly the blue color, which here indicates the vertical horizontal polarization, so which ranges from over the time period from 2020 to 2024. And from this graph, I can able to observe that vertical polarization is the backscattered is significantly higher than the vertical horizontal polarization. So you can able to see from this graph here, and the VH band, that is the vertical horizontal polarization, so which is comparatively lower than the vertical polarization backscattered. So now let us talk about the interpretation of this particular graph here. So VV and VH backscattered time series. So VV and VH represents the backscattered coefficients in decibels, which indicates the surface roughness and vegetation structure. The VV backscattered is consistently higher than VH, typically ranging between -10 decibels to -15 decibels, which suggests a strong surface scattering from the ground and vegetation canopy. And the VH backscattered varies between -18 decibels to -25 decibels, representing a volume of scattering from the vegetation. So both backscatter trend exhibits a seasonal variability with a noticeable fluctuation aligning with the vegetation changes in RVI plot. So the periods of increasing VH and decreasing VV indicates the higher vegetation presence, whereas the decreasing VH and increasing VV suggest the bare ground or spare vegetation condition. So the interpretation or the result of our analysis. So a strong correlation between RVI and VH backscattered confirms that the VH polarization effectively captures the vegetation variation. The seasonal peaks in RVI coincides with the period of higher VH backscattered, indicating a dense vegetation growth, and the analysis provides a clear understanding of vegetation dynamics over time, making it valuable for the applications such as crop monitoring and forest change detections, and even for the drought impact assessment. So now let me get back to Earth Engine. So in our next step, we're going to extract the Radar Vegetation Index for this particular period, that is from 2023 to 2024. So to do that, we're going to define another variable, RVI 2023 to 2024. So we're going to refer this image collection, RVI collection dot filter. So we're going to apply the time series, the time span, for example, from 2023 January 1 to 2024 December 31st. And from that, to obtain a mean image out of it, we're going to define dot mean function. So in order to obtain the mean image out of this entire time period, and next last, to view this image, we have to add this layer. So to do that, we're going to define map.add layer RVI 2023 to 2024 dot clip study area, so based on our study region, and we have with a minimum of 0, and we have to specify the minimum and maximum value. And the color palettes, blue, green and yellow. So blue, which indicates the low RVI value, green, which indicates the moderate level of RVI value, and yellow, which indicates the higher RVI value. And we can output the layer as RVI 2023 to 2024. And last, to expose this processed RVI image to our drive, we're going to define export.image.to-drive image. We're going to specify RVI 2023-2024 and clip it based on our study region. So for that, we are applying this clip function, dot clip function. And next description, we're going to mention RVI 2023-2024 and study area. So I've mentioned our region of interest, that is our study region. And the spatial resolution, I'm going to set to 10 meters because this particular data set has a spatial resolution of around 10 meters. You can able to visualize it from here. So for that, I'm going to mention as spatial resolution as 10 meters. So next, we're going to mention the coordinate reference system, that is EPSG4326, and the folder we're going to export as RVI analysis, and the max pixel value is given. So next, we have to visualize the layer we have analyzed for. So we have 4 layers. So the first is our study area, and followed by the mean radar vegetation index image over the time span from 2020 to 2024. So you can able to view from this image. So as I already mentioned here, so the blue color which indicates the lower RVI value. For example, you're going to turn to satellite mode, and I'm going to adjust the transparency here, so you can able to see the below given the base map here. Let me turn this off, so you can able to see from here. So this is the water areas, so which is clearly indicated in blue color, so which is a lower RVI value. Comparatively, the green which indicates the moderate level of RVI value, and you can able to see from this image. And our next image, that we have created a sub-region. So based on our so this is the list of sub-region. So based on the farmland here, so we're going to analyze the RVI value for this particular farmland. So for that, we have created a sub-region for this particular farmland. So this is our farmland here, so you can able to see that. So for that, we have analyzed the RVI value over this particular farmland. We have created a time series chart for that. And last, we created RVI value for this particular year. So similarly, so this particular RVI value for this year 2023 to 2024. So the blue color which indicates the lower RVI value, and the green which indicates the moderate level of RVI value, and last the yellow which indicates the higher RVI value from this image. So you can also adjust the transparency or the contrast of this image. For example, I'm going to navigate and click this option, and in that we're going to make some changes to it. In the custom section, I'm going to make it to a stretch 90%, and it's going to say visualize the value changes from 0.2 to 0.8, and we can apply this. And now let us visualize the image, so you can able to clearly visualize it now. So all the lower RVI values are indicated in blue color, and the moderate level of RVI value which indicated in green, and the higher value RVI values are indicated in yellow color. So you can able to see from here, see from this image here. So I'm going to close this. And last, we have to export this image to a drive. So in order to export this image, we're going to navigate this option called task section here. And in that, we're going to click this option, unsubmitted task, RVI 2023 to 2024. We're going to click this option called run. And now a window pop up saying initiate image export. Task name is RVI 2023, EPSG 4326, and spatial resolution. So I'm going to set to 10 meters. And we're going to export to a drive, and the file format is in GeoTIFF. And to export this to a drive, you can click this option called run to export to your Google Drive, and from that you can download this image. And you can also export to cloud storage and Earth Engine asset. So to download as a Google Drive, from Google Drive we can export from this option drive, and you have to click this option called run. So now let us take a look at the application of this particular analysis. So agricultural monitoring, tracking the crop growth and assessing the drought impacts, and evaluating deforestation, and for forest ecosystem studies, identifying the changes in forest cover due to logging and wildfire or climatic variability, and urban green space monitoring, assessing the vegetation dynamics in urban environment. So in this video, I have shown you how to create a radar vegetation index using Sentinel-1 SAR Imagery in Google Earth Engine. So the code is given in the video description, and thanks for watching, and make sure that you subscribe to our channel and give us a like.